In this video, we will review the idea of indefinite integrals. Basically, an indefinite integral is just another name for the family of antiderivatives of a function. So, if capital F is an antiderivative of lowercase f on some interval, then we write the integral of f of x dx equals capital F of x plus c. So, this symbol is for the indefinite integral of f of x, lowercase f of x. And if capital F is any antiderivative, we have capital F of x plus c for the indefinite integral. By convention, we assume that an indefinite integral is only valid on an interval, which is basically a technicality. Let's look at this example. I want to determine whether this statement is true or false. Is the indefinite integral of x, natural log of x squared dx, equal to 1/2 x squared times the quantity 1 plus natural log of x squared plus c. In the notation of our definition, x, natural log x squared, is lowercase f of x, and 1/2 x squared times 1 plus natural log x squared is capital f of x. We know this is true if the derivative of capital F of x is equal to lowercase f of x. So we just want to determine whether that's true. So let's take our derivative. F prime of x, capital F prime of x, I'm using the product rule. I have 1/2 x squared times 1 plus natural log x squared. My derivative is 1/2 x squared times the derivative of 1 plus natural log x squared is 0 plus 1 divided by x squared, that's the derivative of the natural log. The chain rule tells me to multiply by the derivative of x squared, which is 2x. And then plus our second factor, 1 plus natural log x squared, times the derivative of 1/2 x squared is x. Simplifying, I have 1/2 x squared times 2 divided by x, canceling a factor of x, plus, here I'll distribute the x plus x, natural log x squared. And in the first term, the 2's cancel and a factor of x cancels. So I have x plus x plus x, natural log x squared, which of course is 2x plus x, natural log x squared. Is this equal to our lowercase f of x? No, it is not. And so, because the derivative of the right-hand side does not equal the function inside our integral on the left, this statement is false. In this problem, we need to find the general indefinite integral. We have the integral of the quantity v minus 2 squared, all divided by the cube root of v dv. We know that we just need to find an antiderivative of the function v minus 2 squared divided by the cube root of v. However, there is no such thing as a quotient rule for antiderivatives or a quotient rule for integrals. So we need to do some algebra to change the way this function is written. So let's first square v minus 2. V minus 2 squared is v squared minus 4v plus 4. That is the top of the fraction. The bottom of the fraction, cube root of v, we can write as v to the 1/3 power. Then I can split up this fraction by dividing each term in the numerator by v to the 1/3. So I have the indefinite integral of v 2 minus 1/3 is 5/3 minus 4, remember v to the first, divided by v to the 1/3 is v to the 2/3 plus 4v to the negative 1/3. dv. And now I can just use the power rule for antiderivatives for each term. So my first term, v to the 5/3, an antiderivative, is v to the 8/3 divided by 8/3 or multiplied by 3/8. For my second term, I have minus 4 times v to the 2/3, adding 1 to the exponent gives me v to the 5/3. And multiplying by the reciprocal of 5/3, I multiply by 3/5. For our last term, I keep the plus 4. I multiply by the antiderivative of v to the negative 1/3, which is v to the 2/3 multiplied by 3/2. And because we need the general indefinite integral, or the most general antiderivative, I tack on plus c. One more step just to clear up the constants. 3/8 v to the 8/3 minus 12/5 v to the 5/3 plus 6 v to the 2/3 plus c. One more example. Let's find the general indefinite integral of the function secant theta tangent to the 3rd theta divided by secant squared theta minus 1 d theta. In the previous problem, we used algebra to rewrite our integrand, which is the function here inside our integral. In this problem, we are going to use some algebra and also some trigonometric identities. Remember, we have the Pythagorean identity that sine squared theta plus cosine squared theta is equal to 1. And if I divide each term here by cosine squared theta, this tells us that tangent squared theta plus 1 is equal to secant squared theta, or in other words, tangent squared theta is equal to secant squared theta minus 1. The point being that we can rewrite the bottom of this fraction as tangent squared theta. So we have the indefinite integral of secant theta tangent to the 3rd theta divided by tangent squared theta d theta. Now we can cancel a factor of tangent squared theta in this fraction, giving us the indefinite integral of secant theta tangent theta d theta. Now, what function do you know that has a derivative of secant theta tangent theta? Well, that function is secant theta. The derivative of secant theta is secant tangent. For the general indefinite integral, we tack on plus c, and this is our answer.